Okay, this is the second part of a presentation about probability and a newspaper competition. So essentially we're at part B. So the first part was quite a long part, so I'll just move back to the first part here. A company runs a competition advertising three newspapers A, B, and C, which have large daily readerships in the proportions 2 to 3 to 1 respectively, and each reader reads only one newspaper. So there's a couple of other things to remark upon here, but I'll just sort of scroll down here to sort of say the probability of A is 1/3, the probability of 1B is 1/2, the probability of C is 1/6. That is to say that the probability of, if you meet a person who reads one of these newspapers, they fall into these proportions, these probabilities. And this is also is in respect to entry to a competition over there, the conditional probabilities. We found that the probability of entering the competition was 0.02. Okay, and essentially what we're using here is a lot of stuff related to conditional probabilities and Bayes' theorem and so on. So just to sort of skip over it. Now, so what is the probability that the top prize and the second prize are both won by reader A? So what we're going to do here is we're told explicitly in the question that large readerships. Okay, so this is really large number of people reading these newspapers. Okay, so in the millions, let's say. Okay, that is relevant here. Okay, so it's sort of not something we could. It's something. It sort of gives rise to an assumption that we're going to use large readerships. Okay, what is the probability that the top prize and the second prize are both won by readers of newspaper A? So this is the probability of winning given that you read newspaper A. So this actually is probability of A given E. And we found that out in the last question there. Okay, is equal to 1/3 in part A. So it's not the probability of A, it's the probability of A given E, which also happens to be 1/3. Okay. Now, there's the sort of, usually what you would sort of think about in these questions is counting problems is that sampling with and without replacement. We could disregard that here because essentially what we're going to say is that we have very large readerships, so we can disregard this finite population correction, as we call it. Okay. That is to say that our answer here is going to be close enough that that extra person that we remove from our sample is the probability of the effect that has in the overall probability is negligible. Okay, so the probability of winning the first prize, okay, is 1/3. Given that the person has entered the competition and won the competition, the probability of the winner coming from newspaper being a reader of newspaper A is 1/3. So we're going to consider these independent events. They are independent events. So the probability of a first prize and a second prize being both won by a reader of newspaper A is essentially an independent event, and the probability of that is 1/3 squared, and that is equal to 1/9. Okay, this is not actually a mathematical question. This is just actually thinking about the problem, really. Oops, gone too far there. So, what is the probability that the top prize and the second prize are won by readers of two different newspapers? So, we have three possible newspapers, okay? And essentially, just think about this. So, the first prize could be won by A, and the second prize could be won by B, okay? But this is equal in probability to the probability of the first prize being won by B and the second prize being won by A. Likewise, AC and CA and BC and CB. So those are the 6 possible outcomes we can get, okay? Now, just as it happens, they're equal to each other. A and B is equal to the probability. A and B, first prize A, second prize B, is equal to the probability of B, first prize B, and then second prize A, and so on for these two. So essentially what we're going to do here is double up. So 2 times each of these here, okay? Just for the sake of simplicity. Well, the sake of speeding up the calculations, but just to sort of be able to recognize that, or what you could do is actually do all six together. This is the key step here: knowing all six possible outcomes of the first prize and second prize being won by readers of two different newspapers. There are six ways we can get that, but there are there are pairs that actually have the same probability, so we can just essentially speed it up a little bit. Okay, so that's what I've done here. Okay, so the probability we're looking for is, this is AB, but it also could refer to BA. Just the order is reversed. Okay, essentially we get the same number, 1/3 times 1/2, or 1/3 times 1/4. If that was BA, that would be 1/4 times 1/3, which gives us the same value. Okay, so that's why we double up. This is AC, but also CA. And this is BC, but also CB. Okay, first prize C, second prize B. Okay, so that doubling up there is just reflected by that 2. Okay, just to save a bit of like space on the page, essentially. That's the only reason I'm doing it. Okay, you could enumerate all 6 probabilities if you want. So 2 times 1/3 times 1/4, that's 2 times 1/12. This is 10 over 36, which is 2 times 1 times 2 times 1 over 3 times 5 over 12. That gives us 10 over 36. And again, 2 times 1 over 4 times 5 over 12. That gives us 10 over 48. Working that out, turn it into fractions over 72. We get 12 over the 72 plus 20 over 72 plus 15 over 72, and that gives us 47 over 72, which just is 0.653, or 65.3% if you prefer. Okay, now that is fine. Now this part here, this was the key part here. Each of the 6 possible outcomes that question could refer to. I've sort of realized I'm going onto the page there, but essentially what we have there is 6 possible outcomes and so on. Okay, so that's part C. Now, but finally down to part D. What is the probability that the top 3 prizes, so 3 prizes in this case, are won by readers of different newspapers? So this is the same thing again. Okay, so we have 6 times 1/3 times 1/4 times 5 over 12. Sorry, let's actually, I'm sort of said this the same way again. Okay, this is 3 factorial even. Sorry, I was going to say 3 choose 1, but it's actually 3 factorial. Now, essentially what we're having here is all the possible outcomes that we can get. So we can have first prize A, second prize B, and third prize C. Or we could have CBA or ACB. Actually, do you know what? I'll just write them all out. BAC, BCA, and CAB. Okay? So that means first prize A, second prize B, third prize C. This one over here means first prize B, second prize C, and third prize A. Okay, so essentially each of these 6 outcomes have the same probability: 1/3 times 1/4 times 5 over 12, and that gives us 5 over 24 when we multiply by 6. So the answer there is 0.208, 20.8% if you want. Okay, now this actually chimes with something that will come up later in the course, which is the binomial distribution. Okay, so in my sequence of videos, I haven't come across the binomial distribution yet, but if you're looking at it after the fact and you sort of see the resonance there, the connection there, it is correct. It's just I haven't got that far yet with my video sequencing. Okay, so we leave that there. So the 3 factorial. By the way, it's not exactly the binomial distribution. There are a couple of key differences here, but it's sort of setting it up towards the binomial distribution. Okay, so that's just a sort of comment about how things dovetail with each other. Okay. Anyway, the key thing here is independent events and the 6 possible outcomes that create that event. So we'll leave it there.